Hey, Mr. Caldwell here. Wanted to talk to you all about forces and charge and how those two connect. There's a nice little formula that allows us to calculate, excuse me, the amount of force that is interacting, that is being generated between two charged particles. And it's a little bit tricky math-wise, but once you get it, I hope that it's not too bad. So let's think about this. I've got a charged particle over here, charge number one, and another charged particle over here, charge number two. And they are some distance apart. Now, if you just kind of use common sense, if they're really close to each other, do you think that that creates a larger or a smaller force? Well, if your teacher is really close to you, they're probably going to be a little bit better able to influence you. So when these charges are really close to each other, they're going to exert large forces on one another, whether it be attraction because they're oppositely charged or repulsion because they are the same charges. So distance matters when we're talking about the amount of force. The other thing that matters is how large are these charges, right? If I have piddling amounts of charge on each of these, like just very, very small amounts, then there's going to be very, very small forces. If I have large charges, then it would make sense for me to have large forces. So when we think of all these things and we try and put them together in an equation, our friend Coulomb, the old French dude who we've not only named the unit of charge after, he was the one who kind of took the measurements and figured out the mathematical relationship here. Now I'm going to use some symbols here. I'm going to use Q1 to represent the amount of charge on object one. And remember, charge is measured in coulombs, which is represented by the letter C. And I'm going to use Q2 to represent the amount of charge on particle two. And distance, we'll just go ahead and let the letter D represent distance. Now, something that is a little bit sneaky, distance is always in meters. Don't do a problem in any other units other than meters. If you use another unit, it'll throw you off. And remember, our charge is Q. Q is in coulombs. All right. So here is the fantastic formula that is going to guide all of our thinking when we're talking about forces caused by charges. So let me go ahead and we'll write it out in words first, and then we're going to simplify it down. So if I ever want to know the amount of force, I have to use this thing called Coulomb's constant, and it's just a fancy number, and it's a number that makes the equation work right, and it relates the charges to the force in a nice, neat way. Charge one and charge two. So we multiply Coulomb's constant times the size of charge one times the size of charge two, and then this is called an inverse square relationship. Inverse because distance is in the bottom of the fraction, so it's inverse, it's inverted. And squared because it's the square. So as the distance gets bigger, as these charges get further apart, think about it, your distance is getting bigger. So you're getting a bigger and bigger denominator. Well, if you have a really big denominator, then you're going to end up with a smaller overall value. It's like if you have well, I think the easiest thing to do is to jump right into an example here. All right. But before we do that, let's kind of tidy this up and write it in a little bit of a shorter way. And this is the way that you will often see it in a physics book, and probably the way you might see it on like an equation sheet, or if you have a formula sheet or something like that. So F is force, stands for force in newtons. We said that it's Coulomb's constant. Coulomb's constant is just a special number. It's 9 times 10 to the ninth, and the units are wacky. Don't get all freaked out about it. It's Newton meters squared per Coulomb squared. So it's 9 times 10 to the ninth. It's quite a large number. And then we're going to multiply Coulomb's constant times the absolute value of charge one. So we don't really get too hung up over whether it's positive or negative when we're determining the size. Positive and negative is very important when we're determining whether it's attracting or repelling. But in terms of determining how large the force is, we just worry about the absolute value, the size of the charge on particle one and the size of the charge on particle 2, Q1 and Q2. And remember, those are always in coulombs. And then we're going to divide that by the distance between charges 1 and 2 squared. That's what the little 2 is. So we're going to square that distance. And remember that that distance is always in meters. All right, so let's see if we can use this for a little bit of mathy type problem solving. So I'll keep that in view. So it says, how much force do a 2 Coulomb and a negative 3 Coulomb charge exert on one another when they are 3 meters apart? So visualize this. One of my charges is 2 coulombs here, and that's positive. The other one is negative 3 coulombs here. And right out of the gate, is this attraction or repulsion? If I have a positive 2 and a negative 3, well, opposites attract. So we're going to have attraction here. And so when we do our Coulombs Law equation, all right, that's determining the size of this force, F, all right? And if you think back to like Newton's laws, Newton's third law says that if one object pulls with a certain amount of force, the other object is going to feel an equal but opposite force. So we see equal but opposite forces here. And now we're just going to write down the numbers. So we use Coulomb's constant, 9 times 10 to the 9th Newton meters squared per Coulomb squared. The absolute value of 2 is 2. And I'll put the coulombs on there. The absolute value of negative 3 is 3. And then I'm going to divide by the distance, which is 3 meters. So these are 3 meters apart. And I have to remember to square that. So that's a common mistake that students will make. All right. So I'm going to go ahead and just do this math. So this becomes 6 coulombs squared. So I've got 9 times 10 to the 9th Newton meters squared per Coulomb squared. This is 6 coulombs squared. And I know that 3 squared is 9. So I'm going to go ahead and write this as 9 meters squared. Now I've got the units on here because I want to show you something kind of cool. Meters squared and meters squared, well, those are going to cancel out. And Coulomb squared and Coulomb squared, those are going to cancel out. And lo and behold, you're left with the only unit of newtons, which should be the unit because force is measured in newtons. So that's fantastic. So now we just have to get in here and do this correctly on our calculators, right? So let me go ahead and cover that up. And let's see here. Sorry for the glare. So 9 times 10 to the 9th. Remember in the other video that I did earlier, we use this E notation. So the EE represents times 10 to the. So I can go 9, starting again, 9 EE, whoop, start over, 9 EE, 9. And that's 9 times 10 to the 9th. And then I'm going to multiply that. So you can see that it's 9 decimal places over. Then I'm going to multiply that by 6. And then I'm going to divide it by 9. So I just work my way across, do the division, and this ends up being 6, what is that, million, 6 billion? My goodness. Or if you're doing it on a calculator that's showing things in EE notation, it might be showing it as 6 EE 369, right? 6 EE9, sometimes it'll actually just write 6E9, right? But we could write this as 6 times 10 to the 9th. All three, right, are representations of the actual answer, right? This is your preferred way of expressing this, 6 times 10 to the 9th, but we never leave a number without units. So this would be 6 times 10 to the 9th. What units? Newtons, because it's a force. So all we did here was just a little bit of silly math on our calculator. And we figured out that this, wow, these don't seem like very large numbers, 2 and 3, but remember a Coulomb is a whomping big amount of charge. So a huge amount of charge, and you've got a huge number here, right? And even though 3 meters is kind of a good ways away, that's a tremendous amount of force. These things are going to be really, really flying together because, again, they are opposite charges and opposite charges attract. All right, so hopefully that helped out a little bit for figuring out the force, but maybe sometimes you have to find not the force, but you have to find the distance between two charged particles. So check this out, all right? Did some crazy algebra here. It's not so crazy, but what I did was I took our original equation, which was force, right? Actually, I'll cover this up so that it doesn't confuse you, right? So I've got force equals K Q1 Q2 over distance squared. And then I'm going to just say, let's solve for D. Let's solve for distance. And so I'm going to multiply both sides by D squared. All right. And so that gives me F times D squared equals K sub C, Q1, Q2. And now I want to get D squared by itself. Since it's being multiplied by F, I divide both sides by F. And at that point, I end up getting something that looks like this guy, right? D squared equals K sub C Q1 Q2 over F, and then square root both sides. So if you don't like all that algebra, don't sweat it, all right? But I didn't want you to think that we came up with this equation out of thin air, all right? It's just doing some algebra. So now we have an expression that allows us to figure out the distance between two charged particles, Q1 and Q2, if we know the force on those two charged particles. So let's look at that as an example. All right, I'll scoot this down here because really and truly, we just kind of need this equation here. So now I've given you an example too. Two charges. Q1, well, this is a negative, and it's not a very big charge. It's negative 3.9 times 10 to the negative 6 coulombs. And charge 2 is 2.1 times 10 to the negative 5th coulombs. They exert a not so big force, 2.7 times 10 to the negative 4th newtons. So we got pretty small numbers here. And the question is, how far apart are they? Well, let's go ahead and since we're asked for the distance, how far, we're going to go ahead and use our D equals square root formula that I've got right up here. And I'm going to go ahead and just plug in numbers, 9 times 10 to the 9th, Newton meters squared per Coulomb squared. And then remember, it's absolute values, so I don't worry about the negative sign here. I do worry about this negative sign. I can't make that go away because that has to do with how big or small the number is. So I'm going to go ahead and just put 3.9 times 10 to the negative 6 coulombs. Because let's face it, a negative and a positive are going to attract to one another. But I am not worried so much about that after I recognize that it's attracting. I'm just worried about the size of the force, in this case, the size of the distance. And Q2, well, since this is a positive 2.1, I'm just going to write 2.1 times 10 to the negative 5th coulombs. And then we divide by, remember, the F, the force. And I gave you the force here, 2.7 times 10 to the negative 4th. 2.7 times 10 to the negative 4th newtons. All right. So again, some math. We get out our calculator. I'm going to go ahead and scoot this on up. And so that hopefully I can squeeze this in here. Yeah, just barely. All right, so 9 times 10 to the 9th. That's going to be the EE, 9 times 10 to the 9th. And then I'm going to multiply that by 3.9 times 10 to the negative 6. So I'm going to go EE. I'm going to hit 6. I'm going to get negative. All right. And then I'm going to do the 2.1 times 10 to the negative 5th. So I'm going to do times 2.1. The times 10 to the negative 5th, that's the EE, so that I go 5 negative. And that right there is the entire numerator, okay? Everything multiplied together. So now you just have to divide by the 2.7 times 10 to the negative 4th. So divide that by 2.7. And I'm not having to type in times 10 to the EE notation, just makes it so nice. So then I'm just going to go a 4, but because it's 10 to the negative 4th, don't forget to put that negative sign on there. And so now that is what I end up with. So D is equal to the square root of 2730. D is equal to the square root of 2730. Now, if I'm looking at units here, right, newtons are going to cancel out. And Coulomb times Coulomb gives me Coulomb squared, which is going to cancel out Coulomb squared. So this is actually meters squared, which is exactly what I would want, because when I take the square root of this number, the square root of 2730, that's going to be all the way down here. Bloop. Square root of meter squared is meters. So these guys are 52 point, well, let's see, why don't we call it 52.2 meters apart? All right. So hopefully this also helps you in maybe reviewing this stuff for whatever quizzes or tests you may have coming up. But nice to see you, and I hope to see you guys soon enough. And be well. Take care. Bye bye.